to learn the potential energy. The goal is to learn the potential energy surface, and there are a variety of methods to do that, starting from like conventional classical molecular dynamics based on like empirical forms to all the interesting talks that we heard this week, which covers kernel methods and neural networks and representation. So today I'm going to basically focus on the smooth overlap of atomic position representation and then the Gaussian process regression and how to effectively do active learning for kernel methods, in particular Gaussian process regression. So once you've learned the potential energy surface, what we can do is we can do scalable molecular dynamics. And what do we get from these MD simulations? We can get the pair distribution functions. And doing a Fourier transform of these pair distribution functions, we can get the structure factors. And from the structure factors, we can either do an X-ray scaling or neutron scaling to get the total structure factors, which is a quantity which can be directly compared with experiments. And once the experimentalists tell you, oh, these quantities match really well, you have a good model, then what we can do is like drive very long simulations and then get the properties that is of interest to experimentalists, like conductivity, diffusion constant, thermodynamics, melting points, phase diagrams, whatever you may need. So I'm going to keep on coming back to this thread of comparison with experiments. So keep in mind the structure factor. So going back to the fitting the potential energy surface, the way I see in my workflow, at least when I started doing this process, is I can divide this into 5 steps. The first step is like getting a lot of ab initio molecular dynamics trajectories and then like curate the most interesting data from those and fit the potential energy surface. And then the next step, you actually run the simulations and do the validation like I showed in the previous slide, and then compute the properties of interest. So where is the bottleneck? So let's identify the bottleneck and then give a motivation for active learning. So there are 2 challenges that I saw. It might be different for different people, but that was in terms of the data preparation. So you can have all the data in the world. Doesn't mean you can fit the model because you have limitations of the resources. It might not be meaningful data, all sort of problems. So first challenge is sample the correct data points and then pick the most interesting points from those pool of data. And then the second challenge is you still have the hyperparameters for these models. You have to figure out what are the best hyperparameters on the fly once you pick the data, the minimum number of data points. So, and then say you have to arrive with those hyperparameters for the chosen data, let's say to a target accuracy. So there are these 2-fold problems. And then eventually this has to interpolate to the properties that you want to measure. It's not just that like if you fit something and then get away with it. That's not the goal. So how do we, so now that I've given you the motivation for active learning, let me quickly explain active learning from a very specific perspective. This is a large field within computer science. So the one that we initially looked at was something which involved like text and image data and all those. When you have a very large pool of unlabeled data, like sentences that are not annotated or images that are not annotated. So there has been conventionally in computer science a lot of literature around active learning around those problems. And then what they were interested in is like arrive at the used active learning to drive a supervised machine learning model, which is in our case GAP or a neural network method or whatever, and then pick the best data that the active learner would learn and then use that to guide the machine learning model to arrive at the best possible accuracy. So within the context of this approach, what we looked at was this paper by Sanjay Dasgupta, where they proposed this active learning in 2011, which is, so there are 2 parts to the problem they were looking at. Like one is like, there are always underlying patterns in the data. So an intelligent algorithm would automatically figure out what are the patterns in the data. The way it does is, it figures out, like, let's say it's a sentence problem and the goal is to figure out like what are the nouns and then the verbs, and then draw a decision boundary to separate them out. So that's how they did this. And then like once you know the decision boundary, which is very domain dependent, and then you can easily separate out the white dot and then the black dots. And then you don't need to sample all the white dots and all the black dots as soon as you understand that there are 2 classes of dots. So in our kind of data, where is the decision boundary? Typically, like most of the data I'm going to show today would be time series data. So the decision boundary would lie, can be extracted from if you plot the time autocorrelation function. So, and that changes with material, with the temperature, the condition. So essentially the hypothesis I'm going to throw at you is that the decision boundary lies at the autocorrelation function. What we are going to do is we are going to use a clustering algorithm that approximates which gives you the width of the cluster from the time series data that approximates the relaxation time. So this is the first part of the data sampling approach is decision boundary and then how to sample the data through clustering. Second, as I said before, figure out the hyperparameters, and that has to be done on the fly. For that, we'll use Bayesian optimization. So what I'm going to do in the next slide is explain the components that we actually implemented for GAP. So to extract the clusters, we actually tested different. We took a model system, and then like what we did was we did this clustering for a model system, and then extracted these clusters and saw which one of the method gives the closest average number of clusters with the autocorrelation function. This turned out to be an algorithm called HDB scan. So what this does is we pass the trajectory to this algorithm and it splits it into n chunks, and then from each of the chunks initially we sample one data at a time, and then the next step what we do is like we do the on the fly for that chosen number of data points we find out what is the best gap model that can be fitted with Bayesian optimization. So in the first iteration, if the data is not enough, what the BO would tell is like please sample more data, please add more data till you reach this user-defined accuracy. So this is how we have set up our workflows. It does not figure. It turns out that you don't even need AIMD dataset, and I'm going to explain through a couple of examples like how we implemented this for a different set of problems. And you will see through the tutorial that how exactly this whole thing runs, and then yeah, you'll get a feeling of what I'm talking about. So before I jump into like application, I'm going to just give you an example. Like actually, so we work with Professor Gabosani, and then like in the beginning itself, he told us like, I want to see this thing actually is better than a human being. Do a handpicking and show me that your algorithm is better than that. So we did that. We took 3 classes of data set for a material called hafnium dioxide, heated it at like 3600 Kelvin, and then quenched it with the melt quench simulation. And then the quench simulation created 33,000 data points. We gave it to a human being for handpicking, and then the active learning to do this protocol. And it turns out the student, an intern, it took 2 weeks to get this right, to reach to whatever accuracy the student kept on doing, and he reached 3 millieV accuracy. Took 2 weeks, and then close to 30 iteration, and then like the algorithm, it took to reach 5 millieV per atom with 11 iteration with under 5 hours on a HPC node. So with just 260 training points. So yeah, that's just a comparison, just to show like, if this thing works or not. And then next step is obviously like apply it to different data sets. And then we found out like for the entire melt quench simulation from a pool of 45,000 data samples, the active learning reached the user accuracy, which is what is plotted in here, which is comparing the energy and the forces predicted by gap on the y-axis, and then the x-axis is the energy, and then the forces predicted from DFT. So it does a pretty good job, and it only needed like the 2% of the entire configuration space. And then, so this is the first part, like it's all well and good, you could fit a model. So does it lead to meaningful results? So with that, we took this model, and then what we did was we did a simulation 64 times the training data set size, which was around like 100 atoms. And we did simulation for 6,000 plus atoms, and then ran simulation 100 times longer than what was done with the melt quench simulation with DFT, and then with a very low quench, right? And basically we got exactly the dotted line is actually, you can see the pair distribution functions plotted here. On the left is for the liquid, and on the right is for the room temperature amorphous form after the quenching. And the most interesting aspect of this material is this hafnia pair coordination. So the dotted line is from DFT, and then what you can see here is that gap actually reproduce the Hafnia coordination predicted by DFT accurately. So the next step is obviously, does this compare well with experiments? Because we have experiments to compare with. So this is, so what I'm going to compare here is liquid structure factors. So the Hafnia melted at greater than 3000 Kelvin, and measure the structure factor is shown here comparing experiments, which is shown in red lines, and then the gap simulations with two different system sizes to show finite size effect. So you can see that gap actually predicts really well, gives a good comparison with experiments. So that's all well and good. So we have only learned a part of this material. So the next part of the talk, what I'm going to talk about, like how do you extend the phase space of the training space with active learning? So with that, I'm going back to the experiment. So we have experimental collaborators with advanced photon source, and then they can do these heating cooling measurements across the entire temperature ranges and get these sort of diffractograms, which is resolved by temperature. They can get these diffractograms. So they said, like, we can fit the crystallographic structures across different temperature and give it to you. Why don't you use that for your active learning? So that's exactly what we did. So the reason for that is experimentally synthesized structure at 3000 Kelvin or 3600 Kelvin is not low energy structure. So if you do a convex hull calculation, it typically would not capture the high energy structures. So this was the intuition of the experimentalist. So they said, like, we can fit this for you and then use that to actually drive the active learning and then the fitting the gap itself. So what they do experimentally is they have aerodynamic levitators at this advanced photon source at sector 6. And then they can aerodynamically levitate small samples and then heat them with laser to greater than 3000 Kelvin. So, and then cool it to room temperature and then measure. They can get temperature resolved measurements across the range of the material with high energy X-ray diffraction. So this is exactly what we took. So they have these pair distribution functions split across the entire temperature region of the material. So they fit few points across this temperature range and then gave it to us. And then what we did was we actually put that into DFT and then gap, and then everything in between. Let's say the experimentalist gave me a point at 3000 Kelvin, 2400 Kelvin, and then like 2000 Kelvin. So we did heating cooling simulation with a partially learned potential energy surface and did iterative training. And of course through the active learner, and then eventually we ended up with a multi-phase potential which can do the entire the crystalline phases, point defects, and then the liquid and then the amorphous form. So we got a multi-phase potential out of this protocol. So yeah, so this as the result from some of the results from that paper were on the top left corner. You can see the X-ray diffraction intensity is computed with gap, and then from the experiments compared 1-to-1, and you can see that the agreement is pretty good here. There are two high temperature phases for hafnium dioxide. One is the cubic phase, which is a mixture of cubic and tetragonal phase. It looks like gap actually figured out it's a mixture of cubic and tetragonal phase, and then like the tetragonal phase, which is the intermediate phase at around, I think, 2300 Kelvin. And then the corresponding three crystalline phases. They also did the neutron diffraction measurements at the Oak Ridge National Lab, and then that's plotted in the bottom panel. So actually the agreement is not too bad. The deviations are coming because that's the limitation of PFT. And you can cache that. That's the beauty of this approach. And then we did the melting point estimation with the gap model, and we got it within 1% of experiments. And then like you can see the entire phase space, the volume phase space reproduced with gap. And then we got a nice paper out of this, which came out in Physical Review Letters early this year. And the entire gap model for this case was fitted with 2000 training samples through active learning. And I'm going to slightly switch track now that I've discussed an experiment-driven approach. We are also working on something called molten salts, which is very interesting class of material, which is important, like in concentrated solar power, in the molten salt reactors. So in this case, what we studied is a lithium chloride melt, And then the way the active learning is set up is slightly different compared to the one that I talked so far. Here, what we do is we learn a gap model from a classical interatomic potential, and we literally like reduce the number of DFT call we need to fit the potential to order of 100 single point calculation. So the way this is set up for this problem is like we just use the standard classical interatomic potential available, which is called the rigid ion model. We get like millions of samples from this, and then we gave it to the active learning, and then we do this. The way we do it is like we superheat the lithium chloride with a rigid ion model, so that like you get a reasonable coverage of the configuration space, and then like we just use that for fitting. And as you can see here, like the force predicted by DFT is compared with gap and then the rigid ion model here. So you can see that actually gap does a very good job and then outperforms the data from which it is sampled on itself. And some of the takeaway here is, so you can sample configurations extremely cheap. It doesn't have to be ab initio molecular dynamics all the time. And this potential was entirely trained with just 584 data points. That's it. And then we saw in the literature, there was another study reported for sodium chloride melts. We have also done sodium chloride melt. I'm not talking about it today because we don't have any active learning in that paper. But so the neural network potential for that case was fitted with more than 100,000 training samples, where the gap model is entirely fitted with 500 training samples, approximately 600 training samples. So that's the entire bit of DFT that we have done for this, for generating this potential. So next question is, there was a lot of discussion I saw during this week that like, is the potential stable for long simulation? So that's one of the points I'm going to address today with an experimental perspective with this problem. And yeah, this was published in Journal of Physical Chemistry Letters. And yeah, again, we have experimental collaborators where they have a different setup for measuring these sort of melts, where they have this cell where they can actually melt, because these potentially they work with radioactive salts. So this is not a radioactive salt. So they have a very tight setup for these kind of measurements for high energy diffraction. And then they've done measurements for the lithium chloride with this sort of a cell which can melt these sort of salts. And what I'm going to do today is introduce a metric that is derived directly from the X-ray diffraction, and then compare the ab initio molecular dynamics and then the gap model with directly experiment. And this is a metric which has been very widely reported in crystallographic literature. If you must have seen, it's called R factor, and we sort of call this beyond RMSE metric because this actually tells you like the model is doing something right. What is R factor? So R factor can be derived from structure factors or the pair distribution function. So as you can see here, what I've plotted here is structure factor on the left panel, which compares the experimental structure factors from HEXRD is the high energy X-ray diffraction, and then the gap run with over 1,000 atoms at 900 Kelvin, and then we found from a paper ab initio MD also, with the same approximation used for our data generation. So it's not that like we are comparing different things. It's the same thing. So at a larger scale. And on the right is the total structure factor, and compared between these three methods. So you can see that gap and then the AIMD agrees really well with experiments. But let's look at the R factor. So what the R factor does is at each of the radial ranges, you can define the short range, intermediate range, and long range, how much of the model, which is in our case is ab initio molecular dynamics, and gap agrees with the experiment total partial pair distribution function. So a larger R factor would mean that the disagreement is large. That's what you have to watch out for here. So we compared for the short range and then the intermediate range. Turns out that gap really outperforms ab initio molecular dynamics. So it has a very small disagreement with experiments at short range and intermediate range. And this is, you have to remember, this is an ionic system. So So this was very surprising for us. So yeah, gap gives you a smaller R factor. And this is actually, and these dynamics are done over 10 nanoseconds. So it's not like 1 nanosecond and then just comparing a short dynamics or something. The potential is actually really stable. We have, for another study, we went up to 30 nanoseconds with up to 10,000 atoms. So another test we did was like, does gap preserve ab initio or DFT accuracy at long time scale? So for that, we did a comparable simulation cell as DFT and then ran for 2.5 nanosecond and threw away the first 2 nanosecond and then took 50 uniform snapshot from the 0.5 nanosecond and then recomputed with DFT and compared. And actually, the accuracy I showed before compared to that, that is plotted in here, DFT compared with gap, it's actually very much preserved the error in the forces. So the reason we did all this is because we want to show that like the active learning is robust and then like it samples meaningful data and then it leads to meaningful results. So that's one of the, and finally, yeah, you can actually do temperature dependent simulations where here, what we plotted here is the partial pair distribution functions for the anion cation, and then cation pairs and resolved by temperature measurement. So you can do this simulations at multiple temperatures at long time scales. And finally, what do you do when you can do long simulations? So we did simulations more than 10 nanoseconds and we computed like first density, and then the density here is compared with the literature values reported in experiments across multiple temperatures. As you can see, there is a small systematic shift that's not huge, but it's because of the PBE plus D3 approximation that used for this simulation is this is what you can expect. And second, diffusion coefficients computed over 10 nanoseconds, and for each of the pairs, and the red and then the blue dots here are from experiments, and then the green and then the black dot are predicted by gap. And finally, diffusion coefficients, ionic conductivities with green Kubo converged over 10 nanoseconds. And then you can see that the trend, it gives actually very close by values. The predictions are pretty good. So with that, I'm going to take a step back and then like explain a bit why we were doing, like you must have seen in all the slides, like it's pretty much everything that we do is pretty much related to experiments. So where are we taking all this active learning and all these things forward? So since I mentioned that I work with the beamline physicists, so what we are interested in doing is build a real-time analysis platform where my boss is actually a computer scientist. So his team actually is working on building infrastructure where like as soon as the experiments are done, the data can be streamed into the leadership class supercomputers at Argonne, and then the analysis can be done with no delay, real-time analysis, and get these pair distribution functions. And complementary to that, we want to deliver machine learning models and then do these pair distribution function analysis on the fly. So this is very much on our bucket list, and this is where we are heading. And we're building software infrastructures to do all this streaming sort of analysis to do this sort of yeah. Because eventually what you may want to do is like steer the experiments to like, let's say, find the right conditions for certain interesting properties and all those stuff. So this is why we think this is an important problem that we should tackle. And with that, I want to summarize, which is, so all the active learning code can be found here. And then I'm going to next quickly go through the tutorial so that you may start the tutorial now. And with that, what I'm going to do is like, I'm going to acknowledge, which is mandatory. So all my research was funded by Office of Science and then the LDRD funding. And I want to acknowledge Professor Gabosani for all his constructive comments and all the help. And then Felix, we've been working with him very closely, and then he's a good collaborator. And I hope he's in this talk today. And a bunch of colleagues at Argonne National Lab include, and a number of experimentalist colleagues also. So With that, thank you so much. I can take some questions if you have any before I jump into the tutorial.
Okay, I see Sean has a question.
Is it in the chat?
Hi. Yeah, so I actually had a question about the slide when you were talking about the results that were more accurate than ab initio MD, I
Yeah.
believe. So was this a gap model that was trained with active learning with
But the same DFT approximation as the AIMD, not the same data set, but the same approximation. It's both of them are like ab initio MD was done in that paper with PVE plus D3, and that's exactly what we use for generating the potential.
Okay.
Yeah.
So it was not experimental data that was training the gap. It was the DFT.
Yeah. In all the cases, it's DFT.
Okay. Okay.
But we can always, like in the first example, the goal was to incorporate. So like you must have seen some of the posters where metadynamics was done. This was our way of incorporating metastable structures into the process of training. I'm talking about the first part of the talk.
Okay.
This one, yeah.
Okay. So I guess my confusion might slightly come from the R factor there because okay, so that's to do with it. That's relative to experiment. Okay.
Yeah.
Because I was understanding normally that you compare, you evaluate it partially by comparing it to how well it replicates the DFT reference data that it was trained on. But now I'm understanding that this is, you're actually saying that the gap model that was trained on DFT reference data more accurately reproduces the experimental results than the data set itself, or a different data set that's trained at the same with the same functional itself. Is that right?
A pure ab initio MD, yeah, compared to pure ab initio MD, yeah. I think there are a couple of reasons why the AMD has a lower R factor here, because I think their density approximation, the approximate density they must have arrived at might not be optimal, because it's just, you must have done it with 200 or 300 atoms. So that's one problem. Yeah. So I think that's a major issue why, well, because you're doing an NPT simulation to relax the structure, right? So you have a better estimate of density and then the relaxation. So the way we do it is through a simulated annealing in all these cases. If you don't have that much of wiggle room with AIMD.
So what is T in this? This is the structure factor?
It's the plot on the right, which is what we are comparing for the R factor. The D of R. Yeah.
Okay, I see. So
It's
because
so the experimentalist prefers to use the terminology total structure factor for some reason. So that's why it's T. Yeah.
I see. So because
sorry,
it's in the interest of
actually
time.
Yeah.
Sorry, maybe we should move on and continue the discussion and gather time or Slack.
Okay, sounds good. Yeah. Let me. Yeah. But
then,
I think everyone can start opening the notebooks. And what I'm going to do is go through a couple of things on the slide before I jump into the screen share with the. So in the tutorial, what you're going to see is a very easy case of active learning, which is like it's a room temperature phase of hafnium dioxide. So it's pretty much like nothing much. There is not much significant diffusion now. So it's very easy to learn. So, and all these data sets are generated at the level of DFT-PBE, and you have about 6,000 snapshot in the trajectory that is in the notebook. And what you will see is that when you're under active learning, you just need 1.6% of 6,000 snapshot to arrive at the accuracy that you've set in the notebook, which is 5 millieV per atom. So with that, I'll just explain the wrapper function that you will be executing. So the reason it's very minimal the way you see in the notebook is because like even this simple case takes like 15 minutes to complete, and I think it borders on the time that we have to finish the tutorial. That's why I made a choice of like, you know, wrap up everything under the hood, and then like you just run and then get an intuition. So going back to the problem that I explained, there are two problems, right? One is a data sampling problem for it, which we use clustering algorithm, and second is on the fly Bayesian optimization. In this case, it's we're going to optimize the hyperparameters of SOAP. So the first line is actually the trajectory information, and then the second is there are like two hyperparameters that actually goes into the clustering algorithm, which is basically to prevent the clusters to collapse into one cluster, which is not what you want, because you basically what you're relying on is the correlation of the time series. So that's why you have these hyperparameters. And second is the definition of the search spaces. The Bayesian optimization is typically done on a search range. So for that, we use the four hyperparameters: the radial cutoff, the number of sparse points, and then the radial and the angular basis functions. And then in the next line is where you define the Bayesian optimization. So this is bare bone. You can see it's just so the first number that is shown here is 3, which means that you're building a Gaussian process regression model over the error metric of the model, which is in this case would be mean absolute error of the fit in the energy. So once you've constructed a basic GPR model with respect to the hyperparameter shown above, and then like with respect to the error as the output of the GPR model, what you're doing is you're going to do something called expected improvement strategy within the Bayesian optimization. And then you'll run 3 iterations of those to go closer and closer to the what would be the best hyperparameters for the chosen data set. And then you would do this process until you reach 5 millieV per atom. This is basically the last line. So this is what you're going to see in the tutorial. So you'll see that this converges very quickly. So there is nothing challenging. So the only thing you have to be careful is this is not a realistic search space. For an actual setup, you would typically run this on a single compute node in a HPC cluster, and then GAP is typically compiled with OpenMP, which would be the setting that I would recommend. And then it's really fast actually. With that, like, you know, you can run a lot of search space within like few hours. For me, like even like very difficult data set like superheated temperature data sets that I shown, it converges within like 3 to 4 hours. So with that, you can actually start the notebook, or if you've already started the notebook, you just have to run it. That's it. Actually, give me a second. Stop share, and then let me go to the notebook. Hope everyone has this notebook open.
So people can follow you executing the notebook, but oh yes, exactly.
Yeah, there is the first is actually just the visualization of the data set, and I think like that would only work on your Jupyter notebook on your desktop. For some reason, it doesn't pop up on DeepNote, but it will definitely work when you actually execute on it on locally. Do you see the screen share? Just gonna run it.
Yeah, we can see that.
I mean, if anyone has questions, they can ask it as this goes on. Okay, started executing. I think it would run about 14 minutes. That's what I found when I checked. Yeah.
So I think Edgar had a question from before.
Yes, thanks. First of all, thanks for the talk. It's kind of a follow-up, still relating
Yes.
to this better performance of the gap-based simulations of pair distribution functions than the reference method. And you said there were some differences in the actual simulation, which might have been the reason for this. But I suppose the kind of more evil way of looking at it is, or the evil question to ask is, how do you know that this is not fortuitous and really a reflection of the deficiencies of your gap model with respect to the reference ab initio potential energy surface?
That's a very good question, because we check multiple, you can get lucky once, right? We check like thrice, 3 different things. So I think for this case, we're lucky because GAP actually does a very good job of modeling this sort of ionic systems really well, especially when it's superheated. So yeah, and you must have also seen in Hafnia, the liquid structure is also predicted really well. So for some reason, we think the liquid structures are across, like the 2 systems that I showed, like 2 independent systems, and the liquid structure is actually predicted really well.
But did you, I guess, out of interest, did you play with running the exact same molecular dynamics setup with GAP that you had already with the ab initio with DFT? Because then I mean, that would give you a measure, I guess, not of the error with respect to experiment at that point, but an error with respect to the reference for the thermodynamic observable.
So even in that case, like there are like 2 limitations, right? Like one is finite size effect. You can't get away with it when you run like 200 to 300 atoms. And second is like the volume relaxations are pretty bad for that case of ab initio molecular dynamics. So I can almost certainly say that like that was the problem.
Yeah. No. So what I'm getting at, I suppose, is by running the exact same setup that you can afford to, which might be limited with the ab initio method, you'd get an understanding of what kind of errors in something like a structure factor you expect due to the imperfect representation of the potential energy surfaces by the gap model, right? By running the exact same setup and comparing those. The same finite number of atoms, same finite run times, and so on and so forth.
Yeah, I have that comparison for the first problem that I showed, because basically everything was started from AIMD trajectory. So for that case, yes, we do have.
Okay.
Yeah.
Thanks.
But sadly, I don't have the numbers on the slide, so which is why I'm not discussing it. So.
Thank you.
Yeah.
So I think Daniel had a question next, if now is a good time.
Yeah. Hi everyone. I'm have a question, but more to the tutorial thing. It's just I'm not very familiar with this gap model, and I don't know if I get during the presentation, but how do you run these dynamics? Is it from lamps, or is this code have this? I don't know the technical part.
Are you asking me if you can run this on the fly somehow on a HPC setup, or like you want to run a section of the active learning would run and then like pre-sample data, and then like everything is orchestrated and launched, and then launch single point calculation? Is that what you're asking? Like everything running like a workflow?
Yeah, I just don't know what platform are you running the simulations after you have the active learning part.
All of them in HPC. Yeah, basically even the tutorial that I'm showing here, it's not realistic, right? So the parameter space that you're sweeping is not even enough for any practical problem of use. So it has to be done through HPC. The way we do it is we mostly, we get a bare bone potential, we just use that potential to sample more configuration and then just directly apply the active learning. That's how we do it now. So
okay.
Yeah, I think the deep potential people do the same, and I think there are a bunch of people who gave talk during the week. I think that's like the common practice now. Once you have a partially learned potential energy surface, you can use the the potential to sample the regions where the uncertainty could be high, which is, I think, one of the speaker was talking about yesterday. So basically, once you have a bare bone potential, then you can use it to sample using the same potential, new configuration, and you just have to pick the minimum number of training points you need to do DFT.
Okay, thank you.
Yeah, and we actually have a package. One of my colleagues is actually working on a package where you can write abstractions for, like, I have like 3 different tasks to run. Allocate me HPC resource, and then like it will take care of, like, it will allocate like 3 nodes for like VASP, and like a couple of nodes for, and a single node for like GAP or any of your favorite machine learning model, and then another node for like LAMS, where you can sample data, and then like it will take care of like this dance between like these 3 different set of tools. I can actually show that here somewhere. I think there's going to be a release of this tool at some point, because basically what I do or what a lot of my colleagues do are funded by HPC research. So we basically, where we are heading eventually is do this on the fly, which we do part of it actually. Like some of the results that I've shown is done actually on the fly with this framework. So it's actually I've taken a lot of this active learning that I showed today and then written it in this format where it can take care of this resource allocation problem. So this framework is called Colmena, and underneath the hood, it uses something called Parcel, which is one of the things that some of my colleagues are developing. So the PDF analysis framework that I shown basically uses this framework where you can actually write abstract in an abstract way, different set of applications you want to run, and then it will take care of, like, allocating the resources and then like this sort of coordinated dance. Yeah. And it's a little too complicated for this tutorial. That's why I didn't bring in any of these stuff. So
I think there's also a question from Chandran.
Yeah, I thank you for interesting talk. I have a question about the diffusion coefficients and conductivity data you show in the last part.
yes.
I see that you have very good consistent results between the your gap model and structure factor, but still I see some mismatch in diffusion coefficients and conductivity. Yeah, even though it is small though. Is there how to improve that accuracy in that transport properties, because structure factor is actually a static property, but conductivity and diffusions are dynamic property. So I see the gap in the transport properties. So how do you recommend to improve their properties?
I think in this case, the only way to get to like the perfect. So there is one issue I didn't talk about. Actually, you must have seen in the ionic conductivity at the highest temperature. There is actually I don't know how to say it. Like it's like a jaw opening, a slight larger deviation. I think I actually checked with experimentalists, and they think that these measurements are done like in the 1950s or 60s. So at that very high temperature point, the uncertainty must have been higher. So that's one factor we should take into account. And second is the only way to get to higher and higher accuracy is probably like increase the approximation that you're using, and then ensure ensure that, like, it gets better and better agreement with experimentalists. So I think that's the only way to do that. And yeah.
Mm-hmm. Yeah, thank you.
So in the density, actually, you can see there is a systematic shift. So that's because like the PBE plus D3 actually under predicts the density.
I see.
Yeah, yeah.
But you can also, you could use different functional or the van der Waals correction to get the correct density, because I feel my understanding is that density is the pretty fundamental property to get correct structural property.
Yes, and there was a poster actually, which actually talked about a similar system. I don't remember who it was, but I think he was talking about very similar molten salt melts. And then what it seems like from that poster, I saw that PB plus D2 is apparently better for these kind of melts than PB plus D3. And D3 is what I've used here. So there are all those factors. So yeah.
Yeah. Oh, I see. Okay. Yeah. Okay. Thank you.
I don't know if I don't know who was the poster presenter, but if he's in the call, I think he would be able to answer also this question.
Yeah, be great if
If there are any other questions, I think people can go ahead and ask them. If not, I was wondering actually. Oh, sorry, there's Piotr who has a question.
But you can go on first. It's okay.
No, go ahead.
But it's because it's not a question. I was just actually wondering if Ganesh could give us, while it's running, give a walkthrough what's actually happened under the hood with this run.
Yes.
AI.
Yes. That's a good point. Yeah. Let me do that. So the first things that you see here is the clustering algorithm actually processed through the trajectory, and what it uses here is root mean square deviations as the distance measure. And then what it has done here is it has figured out like the smallest cluster has 11 elements, and then the largest cluster has like 395 elements. This is exactly the part that I was referring to, which is like the approximate width of the clusters corresponds to that region of the relaxation time corresponding to that region of the time series data. So essentially what you have is like a very variable n chunks of clusters with variable width. So what you would do is like in the first step, sample one data samples per cluster. So eventually, if this, so that means that at the end of the first data sampling, what you ended up was you picked 94 training samples and 94 test samples for validation. So you train on 94 data samples, and then you have an independent 94 samples. You're actually validating 1:1. So the model is verified for every one training data point, an independent test sample is chosen, and then that is what is validated. So, and once you pick these 94 samples, what you do is you're passing this to a Bayesian optimization. And in the first line, what is printed here is like the first choice of parameters the Bayesian optimization has chosen, corresponding to the range that we have specified, right? Like we have specified a range of parameters where we have asked it to look for like what would be the error of the model. So in this line, what you can see is like for this 94 chosen point, for this chosen set of parameters, what is the mean absolute error? And it's not yet scaled with the number of atoms. So what you're seeing actually here is the absolute, the error when validated against these 94 samples. So this would run like for 3 iterations, and then it creates this with these 3 error values, and this the high dimensional parameter space. It fits a GPR model, and then what it do is like it uses a strategy called expected improvement, which is actually in the slides that I showed, and it picks what are the next set of hyperparameters, which would lead to the maximum expected improvement in the error reduction. So that's what you will see towards the end of this tutorial. So let's wait till this runs a bit more. Yeah.
Yeah, thank you very much.
Yeah, typically you would run this for approximately like 25 initial points and then like another 50 points for expected improvement for the exploration and exploitation sort of search. So this is, yeah, how you would typically do in a real world setting.
And this so this test and train configuration, they were picked up from this data set.
Clusters. Yeah.
Maybe I missed what's the size of the data set? It's much bigger than that, right?
It's 6,000, and then the 6,000 data points are assigned to, in this case, 100, I think, 93 clusters. So this 6,000 data points are like placed in 93 different bins, and you're actually taking one sample each from these bins. That's what you're seeing here.
And this clustering is made by this RMS.
Yes.
Okay. Thank you very much. Yes, thank you. It was much clearer now.
Yeah.
Helena, please go ahead and ask your questions. I feel guilty for stealing it from you.
No, yeah, I was also looking at some problems people were having, but I was just wondering, so when you said the experiments, I didn't, maybe I missed something, but I didn't quite understand if you were using them to validate your model or if you actually used some information like actual experimental structures to train the model.
Yeah, we use for all the crystalline phases, the experimentalist can actually fit. So they use something called Lebel, which is a crystallography refinement technique. So they can for that temperature condition, and then for that region of from the PDF, they can approximately fit the atomic positions, and then I think so. They actually do two different set of fits, which is one is from they've done the neutron diffraction and also the X-ray diffraction. So I don't remember exactly which one gives the volume, and one of them gives the volume, and then the other one gives the approximate atomic position. So they do the refinement based on that, and then and fit the coordinate and then give it to me. So that's how we do it. Now the challenge is actually like they can do it very resolved because this is high energy measurements. They can get a lot of data points, but they don't have the infrastructure to process them, the entire phase space. So in the case that I shown, they've only fitted like a few points at different phases. And that's what I've used for driving, fitting the gap with after doing DFT, and then doing the heating cooling cycle with the lamps, and then do the active learning, and then again do the single point calculation and do the refitting. So yeah.
Okay, so it's basically a way of going straight into the correct region of structures you want to represent. Because that's a huge challenge of what you actually put in.
Yes. And also like I see that like Luigi Bonatti is here, and I think he has a very cool paper with Professor Parinello on actually doing this with the structure factors as a reaction coordinate. So that would be one way to do this if you don't have like experimental data and all those stuff. So essentially, yeah, it's a potential learn directly with metadynamics. Actually, for some reason, I can't actually see who exactly is speaking to me because the screen share has taken over and it no longer shows me the other screen. Could be a Zoom problem. Oh, I see. I hope the error got sorted out. Oh yeah, so it could be that the species Yeah, so basically the gap requires E0 parameters. So I've actually patched it through an external file called species.dat. So it should be, it's just a matter of like copying it, copying that file, which basically has the atomic energies for fitting the gap model. I just read it from an external file, that's all. Yeah, sorry for the patchwork tutorial. Oh, that's so strange. I think maybe it could be an earlier version of the notebook that people have cloned. I think Kapil set up the proper one with the deep note. We went through it, so maybe there are multiple copies. Could be why. Okay, so now actually the first three iterations are complete, and it's going to actually set up the GPR model for actually starting the expected improvement runs. Yeah. Yeah, okay, so let me go. So I've actually given an example where like what would be a real world setting that you might really want to run is typically this sort of a parameter space is what you would typically run for a real world problem. And I would like, if you have a high temperature data set, that's definitely where you may want to start because this wouldn't converge that quickly. And yeah. And typically sometimes it would not even get to the tolerance that you may want to set up, right? Like because the DFT might have some systematic convergence errors and that would pop up here. So you would immediately see that like your energy tolerance would be only as good as like what is the convergence that you use for your DFT. So there is unfortunately no magic. Okay. Yeah, Elena, I think maybe there was an earlier version of the tutorial. I don't know. Yeah, so this is actually a very easy system to predict. So it's like this is not even good enough of parameters, but it's already like at should be like 7 milliV per atom. But yeah, there's no guarantee this would lead to any meaningful molecular dynamics. That's the problem. Did anyone manage to finish the run? I think this will take a bit more time, I think, because I started a little bit late. Yeah. Oh, that could be a memory problem. If I think we ran into that because the notebook only allows like a limited memory. Oh, fantastic! Yeah. So I think unfortunately, if it ended up with a larger parameter, I think we had that problem. But if you run this on a HPC node, for sure, like you have no issue. You just have to even like yeah, 128 gigs is more than enough, I think.
So do I understand it correctly that the second the second cell that has, for example, n sparse points between 100 and 1200. That's the kind of parameters you would expect to produce a reliable potential.
Yeah. I think like once you have like a lot, like this is typically just one set of data, right? So, but in a real world setting, you would have like you would want like a different regions of phase space mapped. So typically, so the only reason I do this is because then in the gap fit, actually you have to tag and then give a different set of regularization, and you can specify the number of sparse point independently for each of the like amorphous, liquid. And so this is very useful. That's why one of the reasons why I've set up this way. So basically you have an approximate idea of what would be the number of sparse point if you chose to, use the separate set of regularization in the tag. I think you can see an example here, actually, one of the real world example of how this is done for the silicon case. Like typically you would define this separate sigma, and then you can also define config specific sparse points, right? So this is one of the reasons why I have that parameter in there.
And so just a reminder, you can run the notebooks on the Pro session on Pro machines. Just make sure to not run too long and close them when you're done, because we do pay for them. Well, I mean, Psi-k pays for them, but we have a budget.
Okay. Do you want me to close it or?
Oh no, it's only if you're running on the Pro machines that it charges.
I see.
Right, so the standard machines are free, but the Pro machines have 16 gigabytes of RAM. That's I don't know if that's enough to run these models. That's.
Oh, I see. I don't think. I think we trimmed down the parameter to, and Kapil said that he's not going to do that because we've trimmed down this particular example.
Well, yeah, I have a hard time imagining any, from personal experience, I have a hard time imagining a gap model to be reliable when you only have 4 gigabytes of memory available to train it. Given that
that's true.
Our groups have access to machines with
right, 1 TB and all those. Yeah, typically I train on. Yeah, that's what I also train on. Yeah.
So yeah, I mean, it's a bit unfair if you're not like in a research group that has one of these has one of these enormous high memory nodes. It might be quite difficult to do it. So we actually had multiple requests to update the equip training code to run like on distributed systems like MPI, for instance.
I think actually someone is working on that. No promises about how quickly, but I've heard people talking about
I heard
it.
about this 1 year ago.
It is true. It is currently in the works. There's somebody in our group at work that is working on MPI parallelization of the gap fit codes. So it's in the works, but there is no scheduled kind of release date for it yet.
All right, it's good to hear that it hasn't been forgotten. But yeah, I think it would be very much of interest to anyone who wants to train a gap who doesn't, happen to have access to a 1.2 terabyte machine, which I think is many people in this workshop.
Yeah, there's definitely the restriction at the moment.
Mm-hmm. Yeah. This is not to put anyone off actually using gaps, right? I mean, you can train fairly reliable ones with only a few 100 gigabytes of memory. But I'm sure there are cloud computing solutions or whatever that let you access much higher amounts of virtual memory. Oh. Anyway,
okay.
So we are running into the free work time actually. So we're I think, right? Did we go till 5:30 or 5:40?
30, I think.
Well, anyway, so I mean, you can just leave this notebook open, but just a reminder of the social dinner that we have at 6 p.m. Well, London time, so whatever that is in your local time zone, and whatever meal that is, if you're not sleeping.